Hello, welcome to this eSchool News webcast. My name is Andrew Barlow, and I'm a senior contributing editor here at eSchool News. And I'm going to be acting as the moderator for today's presentation, which is sponsored by Stratasys. And today we're going to be talking about integrating 3D printing into your Makerspace to foster creativity and student ownership of learning. Now, before I introduce our speaker today, I want to take a few moments to highlight a couple of items. First, today's event will be recorded, so you don't have to worry about taking down notes. In a couple of days, we'll be sending out an email to everyone who attends. It contains a link to the recorded event, and you'll also be able to download a PDF of the presentation from that same email. And speaking of the slides for that presentation, if you look at the resource list on your console, you will see that you can also get a Google Drive version of the presentation slides from there. And we've also listed a bunch of additional resources that will be referred to today during the presentation. So if you take a look at these, because once the webinar's over, you won't be able to see them again, I'm afraid. And second, please ask questions. And don't feel as if you have to wait until the end. At any time during the presentation, if you have a question, just type it into that Q&A box on your console and hit the submit button. And I hope we'll have about 10, maybe 15 minutes at the end when our speaker can answer some of your questions. We also have a chat function which you can launch from that blue group chat icon, which you can see down at the bottom of your screen. Use chat to talk among yourselves or to contact me or the eSchool News team with any technical issues or other concerns. However, please don't use the chat function to ask our panelist questions. He's simply not going to have time to monitor the chat. So if you have a question, please use the Q&A panel instead. Now, with that out of the way, let me formally introduce our speaker. Ryan Erickson is the Makerspace coordinator and a second grade teacher at Cedar Park STEM Elementary School in Apple Valley, Minnesota. Before joining Cedar Park, he taught engineering in the St. Paul Public Schools for more than 3 years, and he also spent 6 years in the Minnesota Army National Guard as a Chinook helicopter flight engineer and flew more than 500 hours in support of Operation Iraqi Freedom. Ryan is a huge fan of the Maker movement, and he believes strongly in giving students opportunities that allow them to hold and experience their learning. Welcome, Ryan. It's a real pleasure to have you here today.
Thank you, Andrew, and thank you for everyone that's joining with us today. We have quite the agenda. In getting ready for this presentation, there is so much to talk about around creativity and education, the Makerspace movement, and then really looking specifically at how 3D printers can impact all of our students. And so I would encourage you, if I skip over anything that you want more in-depth knowledge on today, please look at the PDF slides that are going to get emailed out to you later. And please, by all means, get in contact with me through my email address that you'll find in those slides and in the additional resources. So let's dive in. So the big question that gets asked a lot is this: where is the creativity in education? Where is the creativity in my classroom? I want my students to be showcasing their creativity. So this word creativity, for our purposes today, I'm going to use the working definition that creativity is the process of having original ideas that have value. And this is a working definition of mine. I'm always tweaking it, learning from my students, seeing research that's coming out on creativity, but for the purposes of today, this is what we're going to go with. If you want to learn more about the creativity in education and get more information on that, I would encourage you to look at a TED Talk by a gentleman by the name of Sir Ken Robinson. And in his TED Talk, he talks about how as individuals, we don't grow into creativity. All of us, including our students, grow out of it. His main point being that all of our students are creative by nature and therefore have capacity for original ideas that have value, are also known as creativity. A second resource that I would encourage you to look at A great summative article that I found was a Newsweek article back from 2010. And in that article, a psychologist from 1950 from the University of Minnesota named E. Paul Torrance developed a test to measure the level of creativity or creative original ideas that our students had. Over the following 50 years, so from 1950 to 2000, those students were followed to really track their success in life. Overall, the study found that the creativity scores in students were a 3 times higher indicator of success than intelligence. So really getting into this idea of intelligence versus creativity. That study has continued and has since 1990 has seen increasingly decreasing scores in creativity while intelligence scores keep going up. So creativity is going down for the last 25 years while intelligence is going up. And some of the truths that I have taken away from my understanding of creativity are that all students are creative by nature. Creativity is important and should be fostered in our schools. And to foster creativity, we need to allow students to pursue their passions. So now that we have framed some understanding around creativity, let's look at Makerspaces very broadly. So Makerspaces, Fablabs, I'm going to use the word kind of synonymously with each other. So one of the best definitions of what the Makerspace is, I found in an article in Ed Week that talked about the maker movement in K-12 education, and it talked about how making involves attempting to solve a particular problem, creating a physical or digital artifact, and sharing that product with a larger audience. Often, such work is guided by the notion that process is more important than results. To your right of your screen, you see a graphic that I have in my schools, and we have a lot in our schools in our district, by an educator by the name of Jackie Gerstein. And what I love about this graphic, and you can get the link down there if you want this, it really shows that making, or the maker movement and maker education, is a process. It's not about the product. So if that's the case, what is the process in the maker movement to foster creativity? So in an attempt to answer that question of what is the process, or to frame how we conduct Makerspace lessons that foster creativity, I've put together what I simply call the knowledge framework of makers. And we're going to dive in and look at each step. So the first part of the knowledge framework of makers is looking at the goal that we want our students to have from a specific Makerspace lesson. On one side of the knowledge framework of makers, we have what is called command knowledge. And that command knowledge is the knowledge of specific commands and procedures required to run and use tools. So you can think of any tool in your Makerspace or even in like a media lab, and what are the specific things that our students need to know to run those pieces of equipment to their fullest potential. This isn't just about high-tech things, though. Even with my kindergartners coming in, I have to teach a lot of them, the command knowledge of how to use a Lego, what a stud is on the top of a Lego brick and how you connect different pieces together. But that knowledge that students need to use the tool. On the other side of the knowledge framework of makers, we have the strategic knowledge. And the strategic knowledge is concerned with the understanding of the alternate ways by which a specific task may be achieved and the process by which a choice is made. So really wordy, but at the heart of what strategic knowledge is, it's in our STEM school, we call them our habits of mind. So looking at habits of mind, some of ours are, things like persistence, thinking flexibly, thinking independently, and getting our kids to take risks. So really that metacognition, thinking about thinking. And I know in the past when I've been a classroom teacher, this is how we teach literacy. We teach literacy by, as an educator, modeling for the students our thought processes of the decisions that we're making. And this is really important too as maker educators, to model for our students the decisions that we've made so we can come up with those original ideas that have value. And the whole piece with this framework is that at the center of it, you are going to have creativity. When you give your students opportunities to learn both the command knowledge side and also the strategic knowledge side of tools and ways of thinking, this is where students' creativity is going to be fostered. So creativity is fostered when students have the command understanding of maker tools and the thinking strategies to have original ideas that have value. So let's look at some lessons that showcase the different knowledge thinking of these different Makerspace lessons. So for the sake of today, I'm going to show you 3 different lessons: a command knowledge, a strategic knowledge, and a creativity lesson. But know that a lesson doesn't have to just exist in any one of these categories. It could exist anywhere, or it could be, you know, a group of 3 lessons, 4 lessons, whatever the case is. But just for the sake of today, I'm going to show you some lessons that just encompass one. So a lesson that shows command knowledge, so again, the knowledge of specific commands and procedures. With my second grade, or with my second graders, they have a lot of standards around measurement and time. And so my second graders create, they 3D print clocks that they make with a tool called Google Drawing. That clock is then put into Tinkercad, and then we 3D print their clocks. And then they can use them throughout the course of the year with different lessons to help them with that understanding. Now, this lesson, there's not a lot of creative thought in this. There's not a lot of independence. It is a very rigid lesson because if the students kind of stray off and follow what or do what they want to do, their clock isn't going to turn out, and then they're going to be learning you know, something incorrectly. And so for this lesson, I really go into it to teach the command knowledge required to use Google Drawing and Tinkercad to create that specific piece of student work. So on the other side, we have strategic knowledge. So a lesson that I believe showcases strategic knowledge, or at least having students work on those habits of mind. So once again, Tinkercad is a very popular CAD tool that is used to have students produce their ideas. But for my kindergartners, I showcase Tinkercad to them for the first time through kind of a strategic knowledge approach, where they get to interact with it on a very independent, non-rigid basis, but really modeling for them how they can think independently and make some original ideas. But they have no, I don't give them specific things that they're going to create, but this really gets that hook in them that really starts getting them passionate about wanting to create more things. However, if I gave them this without the command knowledge side, they would never be able to produce their ideas because they don't know the specific things that they now need to do in Tinkercad to get their ideas printed. So then moving to the center, we have that intersection where creativity happens. Lesson, and this one's actually 2 lessons that I believe showcase creativity. In 5th grade, there's a lot of standards around around landforms. And so in a previous lesson, all my students learned about a program called SculptGL. And SculptGL is a free web-based program that it's an organic modeling tool. In this organic modeling tool, students can interact with a sphere or a cube and really work with that piece as if it were clay and push and pull and do a lot of different things. Later on in the year, the students have an opportunity to model a landform, but they get to model it in how they choose. And so some of them chose to use this program and model their landform and actually become the natural processes that formed that landform. And then they print it out, and they can actually hold and touch and interact with their learning when they have the command knowledge of how to use that SculptGL tool, the strategic knowledge of how to think independently of how to now use that tool to create their learning. So when we can get our students and our makerspaces to possess both types of knowledge, and so really get into that creativity intersection, creativity is fostered in our students. I would also argue that creativity, or fostered creativity, now leads to student ownership of that learning. And that student ownership increases because making allows students to pursue their passions, see that success comes from failure, and partner in their learning so that it's not just provided to them. Now we're going to move into specifically why I believe 3D printers are such a beneficial tool for our students to do those things that we just talked about. Some of the main reasons, and just to kind of bullet point why 3D printers to kind of showcase our discussion moving forward. I love that for working with 3D printers for students to create their ideas, there is no penalty for innovation. There is no such thing as failure when it comes to 3D printing. Because anything that a student does, they can hold, interact, and learn from it. The second point that I believe that makes 3D printers so beneficial is that 3D printers help students see, or they cross what I call the digital-physical divide. So if I can make something on the computer, I can then have that physical representation of it. And not many tools do that. And so, or I could even build something in the physical world, I could scan it with a 3D scanner, and now I can interact with that on the digital world. I can really go back and forth between this divide of our students really see things as, things on the computer, so the digital, and things that I can interact with in the physical. But as 21st century learners, we know that this digital and physical world aren't as separate as they used to be, but we have tools now that can go in between, one tool being 3D printers. Also, that our students can now become producers and not just consumers. And that's not just with their learning, not just producers of their learning, but producers of their things that they just use in everyday life. And last but not least, I believe that the 3D, not just 3D printers, but the knowledge that a student has to have to produce their ideas, those skills help them or help prepare them for the jobs of today and tomorrow. More and more jobs are being created. More and more jobs are coming up that require students to have design thinking, design intent, and design knowledge, some specific to 3D printers and not, but that understanding of how I can take an idea from an idea to an actual product is really essential. And in all our buildings, I'm sure I'm not the only one, but coding education has become really prevalent in the last couple of years. And you're not going to find many educators out there that would argue with coding's benefit in our students. And I would argue that if we put that much credence to coding, we need to put the same amount of credence to CADing. Coding, is the manipulation and creation of the digital world, so things that exist on computer programs and whatnot. Where CADing is just the yin to its yang, so it's the manipulation and creation of the physical world. And then put in such simplistic terms, I know it's an oversimplification of the definition of what those two things are, but I believe there's power in that simplification, that if we are teaching our students coding, why are we not teaching our students CADing? So moving along, when my district and myself went or looked at integrating Makerspaces and 3D printing into our K-12 curriculum, we sat down and really thought about the process in which we're going to do that. And we asked ourselves really 3 essential questions that I believe can really help you today if you're looking to integrate this, not just in your, maybe you're looking at, a K-12 lens, but maybe you're just a 5th grade or a 7th grade teacher, whatever the case is, these questions are still applicable to you. So the first question is, how do we integrate 3D printing to redefine our students' learning, go beyond just the E? I'll talk about that. Number 2 is, how can students K-12 and even higher ed use CAD or computer-aided design programs to create their learning? And last but not least, what printers best fit our students' design abilities and allow teachers to effectively utilize them. So looking at the hardware. So let's dive into these 3 questions. So number 1, how do we integrate 3D printing to redefine our students' learning? Go beyond just the E. The reason I put the go beyond just the E is because 3D printing at its core has its foundation in engineering, in research, in prototyping within the business world. But we know, and hopefully many of you are interested in, how do we not just do it in engineering curriculum, but say the science, technology, math, art, history. How do we get this so it impacts all of our students, not just those who take engineering courses? Here's just a list of some links that if you really want to dive into this beyond our conversation today, you can get these links in the PDF that you'll be emailed. But here are just some resources for individual individual lessons that go across the curriculum. One I want to highlight, and I want to highlight it because it's just come out. Thingiverse, if you don't know, Thingiverse is one of the largest repository of 3-dimensional designs that you can go download for free and print out. But they just came out with an educational resource that you can search via grade level, topic area, and find some really good resources to at least help the conversation get started in your district and in your building or in your classroom. And that's something that just came out over the last 2 weeks that I'm pretty excited about. So we talk about getting these ideas of integration not just into engineering, but into all. And we really thought in our district that we had to answer this question before we really even dove into getting the 3D printers, because we wanted to have staff buy-in across the curriculum. We didn't just want our students that took the engineering class or the prototyping class to get to be able to be affected by these devices. We wanted all of our students to have the same and equal access. And so really getting that staff buy-in. If you're familiar with educational technology, there's a model out there called the SAMR model, and there's just a little image of it. But that SAMR model, in short, talks about the different levels of applications for using any type of educational technology, but really the effectiveness or the impact that how we use that technology has. And so I have a couple questions, see if I can get them going here, that you can ask yourself that really go from least impact to most impact with your students. So the first one is, how can students interact with CAD or computer-aided design to enhance their learning? What do your students or they already make that they can now make with 3D printing? How can students demonstrate learning through project-based 3D printing activities? And then last, what can students make that they could never make before without the use of 3D printing? So some ideas just to get some thoughts going to maybe bring back to your teams. In kindergarten, one way we've integrated 3D printing into that curriculum is by having our students interact with Tinkercad using a program called Print Shop on our iPads, where students can draw, they can take a picture, and they can 3D print. I have a 15-month-old daughter, and she can scribble on a piece of paper. I can take a picture of it, and my 15-month-old daughter can 3D print. So there is no excuse that you can't use 3D printing even with our youngest students. But this allows even our youngest students not just to start learning about the technology, but to hold their learning, their understanding in their hand and take ownership of it. So in second grade, similar to one that we talked about before, my students also create other tools that they use in class. So here's another way that all my second graders in my building have rulers that they have created from scratch using Google Draw, printed, and now use on a daily basis in their second grade classrooms. And they all own that understanding of how to use measurement, and that understanding is theirs now. And they get that ownership piece is so important, because now they take that ruler home and they're just excited about that learning. Moving on up, fourth grade, science standards around sound, energy, and light. Light is easy for my students to understand because they interact with it every day. Heat, energy, they can still interact with it, but that sound piece, we interact with sound all day long, almost to the point that it's not as interesting for our students. And so what we've had our students do is they use QuickTime and they record their voice as saying a couple words. We turn that audio recording into a waveform image, and then we can turn that image into a 3D print. And so my students can now, which they could never do before, actually hold their sound in their hands. And they can feel the pitch, the intonation, how all these different things, the syllabication affects their words because they can see it. And we're starting to even have in our district, some of our ESL teachers use this with their students, and even on words that are being really difficult. And now we can have them record, 3D print, and use that print to help them in that learning. The next one, already mentioned it briefly, fifth grade, having students create their understanding of landforms through becoming a natural process. So if it's erosion, I'm going to push into that cube, or if it's deposition, I'm going to pull up that cube. And so the students can own that understanding because they not only become the natural process that made that landform, they can now 3D print out their learning and hold it in their hands and now share it with others. Moving to seventh grade, we have our seventh grade history classes. Learn about the rise and fall of the Berlin Wall in East and West Germany, but really learning and thinking about the sentiment of the time, or the sentiment of the people at the time, and their thinking about the Berlin Wall. And so to show their for the students to show their understanding of what was going on at the time, the students have to build in Tinkercad a memorial to the Berlin Wall that quantifies the sentiment of the people towards it. Next one, in high school and various chemistry classes, they use first an online repository called NIH Print Exchange, where students can look and download molecules, chemical compounds, biology models. And so that's important for them to be able to interact, but can we go beyond that? And what they've been doing is to understand Lewis structures and Vesper theory. They've been using a program called JMOL, where the students can actually take in individual chemicals at a time, create the chemical compounds, interact with them in this 3D viewer, and then subsequently print out their learning, or 3D print out those models. And so the image that you see was done on some higher-end 3D printers, but even if you don't have ones that can do color, you can still print them out and have the students paint them and have the students interact with them. But the students own that understanding of Vesper theory, and then we even printed what the Zika virus looked like, because the students were really interested in what that was. And then finally, in high school, students and teachers that have limited interactions with CAD programs can still use a simplistic modeling tool like Tinkercad. And in this lesson, the students were learning about the correlation between surface area and volume. And to demonstrate their understanding of surface area and volume, they had to make containers that held a specific amount. I believe in this case it was jelly beans. And they were able to use Tinkercad to put in the measurements to their containers and then print those out and actually test out their learning to see if it worked. And then they got to eat the jelly beans at the end, so of course they were pretty happy about it. So the next essential question was, how can students K-12 use CAD, stands for Computer Aided Design, programs to create their learning? So if you Google or just look out in the World Wide Web, CAD programs, you're going to find a lot. And you're going to be, if this is, your first interaction with 3D printing, you're going to see, lists that look like this one. And this is just even a snapshot. There's many, many more. But looking at this list, thinking of questions of, what is age appropriate for my students? what budget do I have? Because some of these cost, you know, a lot of money, and some of them are free, but really which ones are going to be appropriate for my students and their learning? And to help us think about this, and I know I mentioned before that we looked at this problem with a K-12 lens, but again, even if you're not in a K-12 position, I think this is still really important. And we looked at this problem and developed what we call, you know, a continuum or a scaffolded model of CAD education from our youngest students all the way, you know, through our 12th grade graduating seniors. With the thought being that when my students leave my school and then go to the middle school, that their CAD education can have a seamless transition, and then the same thing from the middle school to high school. But how do we look at this really the same way that we look at literacy education? How do we have to build that scaffolded model into it? And so our scaffolded model looks like this, and let's see if this will pop up for you guys. We start with our students by modeling through drawing, and then they move to box modeling or solid modeling, and then they move to parametric modeling. And so we're going to dive into what each one of these steps looks like. So this continuum of CAD education, our students K-12, no matter if they're just starting in kindergarten or if they're being introduced to you know, 3D printing CAD education for the first time as 10th graders, they start by looking at a program called Print Shop. And Print Shop is an iPad application that allows students to draw on a piece of paper, take a picture of their drawing, and then 3D print it out. And this can be done within one class period, so it's fast, it's efficient. Students really get excited and start getting that hook for this type of learning instantaneously, right away. And so this is a picture that I had of one of my third graders draw something for me that represented symmetry. So the student drew it, we took a picture, and we were 3D printing it within 5 minutes. So the next step in about first or second grade, depending upon the student, or after they get the introduction of Print Shop, then we move to Tinkercad. And Tinkercad is a box modeling program. And so students start with this box modeling program with a blank slate, call it the kind of the edit screen, but then students drag and drop solid geometric shapes onto the edit screen that they can make larger or smaller, but then they can also combine these to make really complex things or really simplistic things. And so you see on the left a model of a castle, and on the right you see a very simplistic model of wheels and axles. So moving from Tinkercad, thinking about how our students learn and kind of building on their CAD understanding, and around the 4th grade, introducing a solid modeling program called SculptGL, or another one is called SculptTreece. We've talked about SculptGL a little bit before, but again, SculptGL, it's free, web-based. I love it because it works on my Chromebooks. You don't have to download anything. Students start with a sphere or a cube, and just like if it was clay, students can push and pull their models very easily. And you can download the model and 3D print it. And so on the left, you see an image of a 2nd grader's design for an anemometer. And on the right, you see a student pulled in a model into SculptGL, a model of the Grand Canyon. And so they were learning about topography, and they were able to look at and interact with this model of the Grand Canyon to really see like the depth and the different intricate ways that the river kind of meandered back and forth. So in that last step then of this continuum of CAD education, we have what's called parametric modeling. And so 2 parametric modeling tools. One's called Inventor. Another one that I want to highlight is called Onshape. So in brief, parametric modeling, where like Tinkercad was a solid modeling where you dragged in solid modeling shapes, parametric modeling, you start with two-dimensional designs that you have to put in measurements for each piece, and you add parameters, so that's where it gets the parametric parameters to the model. An example would be if you were designing a house and you attach the parameters of the walls of the house to the roof, and if you change the pitch of the roof, all of the other parameters of the walls would change at the same time because those two different dimensions are tied to each other. Onshape, so the pictures that you see on the left is Autodesk Inventor. My school has used Autodesk Inventor heavily in the past. Autodesk Inventor is used by a lot of professionals, but it does cost. There is a subscription fee to it. One that I want to highlight on the right that my school is actually transitioning to using exclusively is a program called Onshape. Onshape is another parametric modeling tool, but the beauty of Onshape is it's entirely cloud-based. It can be used on your iPads, Chromebooks, MacBooks, whatever you have. It's free, and they have some really good educational curriculum that goes with it. So I'd encourage you, if that's interesting to you, to look into using Onshape because it's free. It can be used on all devices, which I know all of our schools have more and more devices, but Autodesk Inventor only runs on Windows-based computers. So the last question, and I don't want to put it at the last because it's the least significant. I actually think it's really significant or really important, is what printers best fit students' design abilities and allow teachers to effectively utilize them. So if you were to go into Best Buy looking for a laptop, you know the kind of the language of what makes a good laptop a good laptop. But what's the language that makes, a good 3D printer a good 3D printer? There's really a vernacular to this type of technology, and if you don't know what all of these terms mean, it's really easy to be kind of blinded and look just at price. And I'm here to tell you that price is about the least effective measure of a good 3D printer out there. My district went with kind of the cheapest ones at first, and very quickly those cheapest ones have found their place on the shelf because they don't work. So let's talk about some of the important factors of 3D printers. So the first factor is FDM. FDM stands for Fused Deposition Modeling. It is really the process that you probably think of when you think of a 3D printer, laying one layer of plastic or fusing it, depositing it on another, FDM. So the next important piece is the build volume. You want a printer that has a large size or large build volume. We are not hobbyists. We are educators, and as educators, I know in my space, when I have 30 student things to print at a time, I want to be able to fit as many things on a build plate, it's called, as I possibly can. I don't have the ability to stand at the printer and take a print off of it every, say 45 minutes and put a new one on. I want to load it up, walk away, say come back, say it's a 5-hour print, and then it's all done. I think that build volume is really important. Another thing you might run into when looking at 3D printers is what's called a heated build plate, and HPB for short. We've had 3D printers in the past that the build plate, some 3D printers heat it up so the plastic will stick to it more efficiently, or will stick to it better. But we've had printers in the past that build plate that's about 100 degrees Celsius is exposed to the world. And we've had some issues in our middle school where these printers were at that students were, you tell them not to touch it, they're going to touch it. And so having that safety concern of not having an exposed build plate or heated build plate is really important. So looking at 3D printers, a lot of these factors that I'm going to talk about I've learned through failure and learned by getting printers that ended up not working out. So one print head. So the print head is the place that the molten plastic comes out of. We've purchased ones in the past that had 2 print heads, and we were like, oh, we're so excited we can run, prints that had multiple colors. But we found that when you have a printer with multiple heads that's not a professional grade model, that now, say, a print that used to take an hour doesn't take 2 hours and now might take 4 hours. And so the time that a printer, or the time that it takes to print a model with 2 different colors for these desktop lower end models, I would suggest just currently the technology to stay away. So if you look on like Indiegogo or Kickstarter, there are hundreds of 3D printers out there. And I would highly recommend that if you want an effective model of implementation in your district, to get printers from an established company, not just because the printers more likely are going to work, but because of the customer support that is going to be needed for the eventual maintenance of this. And I know in my district, the support of these devices actually falls on me as a classroom teacher. As my district's tech department, they don't know really anything about these devices. So as a teacher, I want to have the most effective support as possible. The next one is size options. I want to be able to have printers that have different size options. So a smaller one, say, in a kindergarten classroom, or I want bigger ones that can produce bigger things in my high school. And we'll talk a little bit about that next. Having printers that are not just a printer, but has the entire ecosystem built into it. I don't want just an off-the-shelf, I can buy it and have everything prepared for me, but some of these printers, when you buy them, they don't come with the software that is required to use them. You might have to use a third-party software, and they might say that all these third-party softwares will work to run the printer, but those third-party softwares are not necessarily created to best utilize that printer. And so having a printer that has the software comes with it, the software is made to run that printer exclusively. Continuity, K-12, it really speaks to the size options, but also back to how we talked about that scaffolded approach to CAD education. I want also a scaffolded approach to the hardware, so when my students leave my building, they don't have to relearn the hardware side, so they can focus on their learning for what they're producing and not the learning that's required to run the machine. Print cost over printer cost. We've purchased printers in the past that were on the cheaper end, but then they required, or that printer required proprietary filament, so the plastic that's used, that was incredibly expensive, and it made the initially cheaper printer cost more for us long term. And with all those things being said, my district chose to go with K-12, a Stratasys Makerbot approach. And so Stratasys is actually based pretty close to where I'm at, out in Eden Prairie, Minnesota, and they purchased Makerbot about 5 years ago. And they have a package that can provide my K-12 school system to fit all of our students' needs and to produce all of our students' designs. And so at our lowest level in elementary school or primary, you'll see here coming up the different systems that we implement. So we have what's called the Makerbot Replicator or Mini. Makerbot just actually this last week came out with another one, and I haven't updated this slide, but it's the Replicator Plus, and it's pretty cool. It's cheaper. It's only about $2,000. Pretty amazing machine. I wish I could get my hands on one. Makerbot Digitizer, which is a 3D scanner that our students can make something out of clay, scan it, print it, change it, do some really cool work with. And now we're getting into some of the Stratasys line of products. So the Stratasys Mojo is a printer that can print with what's called soluble support material. And so there's actually 2 print heads on this. And so this is a non-consumer. This would be considered a professional model where my students' designs can get printed with a soluble support material in them. And so they can actually make things that move once that soluble support is dissolved really out of that model. At the middle school, we have still those same machines from the primary, but then we add what we call, or what Makerbot has called their Z18, which is just a much bigger build volume printer. So as their design abilities increase, the size of their, we want to have the capacity to print bigger and better things. Same thing with the Mojo at the elementary level. At the middle school, we have some subsequently bigger machines that can print bigger things. And then in the high school, still that same package, but running also with a Fortis machine that's just larger, more precise, can do some really cool things. And the robotics teams have got incredible use out of printing parts for their robotics out of that Fortis printer. And so last but not least, as we're kind of wrapping it up, we barely scratched the surface of all the different resources out there that you can utilize to run your program in your school. And so in the resource list, you can get to this page by clicking on that additional resources. And I would motivate you to go look at the CAD educational resources. There's about 45 different websites, resource locations that most of them are free, that you can dive even further into your understanding of this. And so that about wraps up my presentation today. I'm going to hand it back to Andrew for the question and answer time.
All right, terrific. Well, thank you so much, Ryan. That was really fascinating. And you know, there are a lot of questions that have come in. Some of them are sort of technical and spec related, and if we don't know the answers to that during this presentation, you know, if you ask a question that's asking about a particular operating system or something and are unable to answer it, we'll have someone follow up with you directly and get you the answer to your question. But Ryan, to kick off, why don't we talk a little bit about, there have some questions that come in about, you know, how many printers do you use in your district, and how many printers would a school need for them to be a resource for all the students? Do you have a sort of a ratio that you find has worked in terms of students printer?
Sure. So to give a kind of an example onto that, you know, it really is based upon the level of use that your students are, you know, having with, you know, this type of education, CAD education. And so I'd say on one end, when you're getting your students kind of up to speed and you're getting your staff kind of acclimated to using and integrating this technology, you know, we've even had in some of our larger buildings starting with just one printer, because it gets them thinking, it gets them excited, it gets them starting to see the potential that these printers have for not only themselves but also their students. But then, so like currently our high school, which is about 2,000 students, they have a very robust program in their Fablabs. So again, that Fablab Makerspace, but they run about 10 3D printers that are going all the time, because they're being used not just in their engineering curriculum, but they're ever increasingly being used in more and more content-based classrooms. And I believe they're even on the hook for purchasing some more. And so, you know, you can start with one. I don't have a specific ratio, but even just starting with one and be able to build out from there. I know right now my elementary school has about 800 students in it, and I can effectively meet all of my students' needs running about 4 printers. I'd like more, but I can manage with about 4 or 5.
Okay. All right. Great. Well, on a related topic, can you talk a little bit about print time? How long does it take to, I know different objects are going to take a different amount of time, but can you give us a sort of a benchmark as to what kind of print times we're looking at?
Sure. And so, you know, this is a really hard question to ask, because there's a lot of factors that go into print time. You know, the size of the item that you're printing, but then also how dense are you going to print it? Are you going to print it hollow, or are you going to print it all the way to solid? And what I would say to that question is that print time, to me, is one of my least, I don't put a lot of credence to it, because with these printers that have a larger build volume, I can load, like the Makerbot replicator, it has a very large build volume compared to other 3D printers of its size, but I can load it up with, you know, say, you know, it depends on the size of the student's prints, but anywhere from, you know, 10 to 15 or 20 students' things on one thing. And I'll set it up as I leave, you know, to go home, and I'll come back, you know, in the morning, and it's done. So it doesn't matter to me that it's working, you know, it might work for 18 hours straight, but it can go 18 hours straight through the night. And I don't need to be there to manage it.
Okay. Okay, great, thanks. To follow up on that, another member of the audience had a specific answer, a question, sorry, about the kind of success you've had with the Mojo. He said experienced long print times and also complained about the filament, the price of the filament cartridges. Can you talk about the experience with the Mojo?
Sure. So you're right. When you get into the Stratasys, kind of the professional grade 3D printers, the price of the filament does increase, significantly and drastically. And the way that we have, or the approach that we've taken to that is by thinking around how an engineer would have multiple iterations of a product. And so my students might produce, say if they're working on, I don't know, a solution to a problem and they've developed this thing in Tinkercad, we might print, 3 or 4 iterations of it on a Makerbot, on the Makerbot system because it is much more cost effective. And then once their design is finally realized and ready to go and has been tested and approved, then at that end, we might finally go to the Maker or the Mojo or some of these higher systems that our middle school and high school have. But then that being said, I use my Mojo, in that capacity. It's not printing all the time. I use it, really effectively when I have something that needs to be, of good quality. I need it to be, done, and maybe it has moving parts because the Makerbot replicators, you can't print anything on those really that have, moving parts, within it. And so really it's a question that you have to ask yourself of when it is effective to use the Mojo over, or these other professional level systems over the Makerbots, but really looking back at what I said originally is that multiple iterations, and then we'll only do like the final product on these higher end systems because we know that that's going to give us the best results.
Okay, terrific. All right, thank you. I just want to talk about the operating systems that will work best for this. We had one question from someone who's saying, what program can be used if you don't have a Mac? And you did make reference to a cloud-based product, which I think was aimed at the higher end. How important is a Mac, or can this be done using, I think you made reference to Chrome, can you do this with a PC? Right. Can you do this off an iPad or a MacBook Air? What do you really need?
So there are no programs that I've run into that need a Mac to operate. Traditionally, it's the other way around. There are programs out there that need a Windows-based computer to run. Some of the ones that come to mind are the more professional level 3D printing CAD software like Inventor, SolidWorks, and things like that. But knowing that in my district, we are getting more and more Chromebooks. The Chromebook initiative is, hit our district hard. A lot of our students are getting iPads, and so really focusing for us, finding ways that our students with these new devices, Chromebooks, iPads, to be able to produce their designs. So some of the programs that I've mentioned, Print Shop. Print Shop is really the only one that I've talked about today that has to be run on an iPad. I would hope someday that Makerbot would produce an Android-based version of it or a cloud-based version of it, but currently there's not. But getting into Tinkercad, that can run on a Chromebook, that can run on any device. I don't believe it can run on an iPad because it is Flash-based. But then on the professional side, but even that program Onshape, I started introducing Onshape to my students in 5th grade, and that can run on, I can run it on my phone that I'm talking to all of you on right now, and that's really beneficial for our students because they can run them on their iPads, their Chromebooks, whatever device they have, they can run it. Now, to actually run the printer, you're not going to be able to do that on a Chromebook because for most of the case, you're going to need a Chrome or a computer that can hook up to your printer. For the Makerbot side, I can wirelessly send my files to it, but you do need to download the software. So you're going to need either a MacBook or a Windows computer. And then for the higher end Stratasys printers, you are going to need a Windows-based computer to do that, and either have that hooked up to the printer or have the printer networked into your school system.
Okay. All right, good. Well, let's transition from the operating side to the pedagogy side. Someone was wondering if you had a sample lesson plan or sample lesson plans that you could share for K-5. Is there somewhere where they could get that?
I do know, and so part of my summer job, I do some work for Stratasys as an educational consultant. And on the Stratasys education page, I believe they make you fill out a form, but there are K-5 lessons directed at introducing, 3D printing into your classroom, but then also looking at that Thingiverse education. And so you can look at, what grade level, your students are, and find and really search for lessons that match up if you have third graders or fifth graders, whatever the case is. And so that's a resource, but also on the Stratasys education page, you can get resources that way. And if you ever have issues, please keep my contact information, and I can help direct you in the right direction down the road as well.
Okay, great. Now, during the presentation, you talked about your young daughter scribbling things down, and then you printed it. And correct me if I'm wrong, I believe that was Print Shop that you used to do that. And then later you also mentioned something that involved a chemical analysis of chemical structure or something. What was the program that you were using at that point?
Sure, let me see if I can go back to the slide real quick. And so all of these resources, these different programs, if you go into that educational resources link on Google Drive that you have, all of these are laid out in that. So there's a kind of a description of what the resource is and how you can use it. But the program that we used was called JMOL. It's web-based, can be used on Chromebooks, and the students, like I said, can drag and drop chemical compounds. You can pull up the periodic table, and so you can get anything that you want. I mean, I'm not a chemistry teacher per se, and so I can't answer specific questions on how our chemistry teachers utilize this, but I found this process for them of using JMOL and being able to export their chemical compounds and be able to 3D print them. So JMOL is J-M-O-L is the program used for that. And then the one above was called NIH 3D Print Exchange, and that's more of a repository, a resource for chemical models, compounds, and things of that nature. Okay,
great. All right, we probably have time maybe for one more question, maybe two. But now, Ryan, you teach in a STEM school. Could you talk a little bit about the difference between a lesson for an engineering type lesson and a lesson for a sort of a Makerspace type lesson? What are the differences that you see in those types of lessons?
Sure. And it's a tough question because they share a lot of commonalities, and and I've had this question in the past, and so thinking about it, the easiest division that I can find between a Makerspace lesson and an engineering type lesson is where the kind of underlying question that gets posed to the student comes from. So like in an engineering lesson, the problem or question is posed to the student from an outside resource, whether it's a problem in the community, in their school, a problem somewhere in the world that they then go out and try to solve, dealing within specific constraints. On the Makerspace side, the difference would be that the questions or problems I would say are posed by the student for the student. And so the student might pose the question of, okay, how do I now use, or I want to make X, how do I do that? And so there's still a lot of questioning and problem solving and figuring out, but it's a student-generated problem and not a worldly generated problem.
All right. Terrific. Well, thank you for that. And I'm afraid that's about all the time that we have left today. If any of you did ask a question that we didn't have time for and we didn't answer, someone from the Stratasys team will follow up to get you some answers. And again, Ryan made reference to a lot of resources and had some web links for you to go explore. We'll have those in the email that we send out to you, and they're also in the PDF and the Google Drive document that he shared beforehand. So if you want to follow up with those will be available to you. So as we wrap up, I really want to thank Ryan Erickson again for a really fascinating presentation. And on behalf of eSchool News, I would also like to thank Stratasys for its support today. So one final reminder before we say goodbye. We will send out an email to everyone who attended when the recording of the webinar is ready. So thank you, and this concludes today's webcast. Goodbye.